So far, we have discussed the different tools for representing the design specification. Today, we shall look into the design process, and there also we shall see how the different kind of representation schemes are adopted to carry on with the design. Fundamentally, an embedded system design implies both hardware and software design. Although there are other aspects of the design which I had already mentioned earlier. So, hardware-software co-design means joint design of both hardware and software architecture. This implies that we need to do hardware and software partitioning. Hardware and software partitioning deals with the assignment of parts of the system description to heterogeneous implementation units. So, when we have represented the overall design, then we have identified the different components. If you remember the UML representations, we have got, say, the activity diagram, which has represented the different tasks along with the concurrency indications. The task diagram is also a specification of the tasks that are to be performed in a system to meet the functional requirements, as well as the constraints can be imposed there. Now, once we have that kind of a representation, we need to map these into hardware and software. Now, mapping into hardware means designing or use of special purpose hardware like ASICs, or it may be even mapped onto FPGAs, and FPGAs are also used for rapid prototyping. If we are talking about the software, the parts or the tasks which get mapped onto the software, it means they are being mapped onto a standard embedded microprocessor or a microcontroller. So, software part of a task is typically mapped onto a standard microcontroller that you are using. Those parts of the tasks which gets mapped onto the hardware, they gets mapped onto ASICs or any other special purpose hardware. Also, we would look at the memory and other requirements through this process. So, the key issue for an embedded system design is this hardware-software co-design, which implies hardware-software partitioning. So, partitioning tasks' basic aim is to find a final design that fulfills all the specification requirements, functionality, goals and constraints at minimum cost. You can understand why this partitioning requirement will come in. If we can map everything, all aspects of the tasks onto an embedded microprocessor or a microcontroller satisfying all the constraints, the most significant constraint will be the timing constraint, then obviously I don't need to use a special purpose hardware. The question of mapping of the task onto special purpose hardware will not arise. Also, it may be the case we might need to select an architecture for doing the software mapping. That becomes what is called an architecture mapping problem. Okay, that means which processor to use, simply put in which processor to use to realize certain functionalities in software. So, that means after we have finished the partitioning, we actually should get a design which is likely to satisfy the design constraints as well as provide the target functionality. The traditional strategy would be an experience-based design, that is, you manually use it, try to analyze and do it. Now, this experience-based design may also involve usage of variety of computer-aided design tools. On the other hand, you can think in terms of a completely automated strategy where you get a computational framework for partitioning and the task can be done completely in an automated fashion. So, design process involves therefore task modeling, using any kind of modeling tools. Then task level concurrence identification and management, which tasks are in the final system, how the tasks are to be put in concurrent models or concurrent modules. We also need to do task level transformations. Transformations which are outside the scope of a traditional compilers maybe, or even if they can be done by the compilers, you should know what kind of transformations are possible which can be applied to the tasks. What are the objective of the transformations? Objective of the transformation to make the system more efficient. That should be followed by the hardware software partitioning. That means till this point we are dealing with the task representation. We are trying to derive an optimal representation of the task. Then we should look at the hardware software partitioning, that is which operation is mapped to hardware, which to software. In fact, when we look at use of automated tools, many of these transformations and the partitioning aspects can be put together and combined as part of facilities provided by the tool. Next, when you have mapped onto this hardware and software, you need to do compilation, because you have got a code which has to be compiled and mapped onto the actual processor. So this is what we call hardware aware compilation, that is making the compiler aware of the hardware features. Then we need to have scheduling, that is sequence of task execution of the tasks such that the constraints are satisfied. How to schedule the tasks. The scheduling of the task would also mean scheduling of the tasks, if at all required, on the special purpose hardware. Now all this process involves what is called design space exploration. Design space consists of alternative possibilities. Okay? So we need to search among these alternate possibilities to find out a design which not only meets the functional requirements and satisfies the design constraints, but maybe cost-wise minimum. So take an example. If I am using for an application a 32-bit processor, with a 32-bit processor like ARM, I can definitely meet my timing constraints. So that is one design option. There could be other design options. Another design option could be using a 16-bit processor and use maybe a special purpose hardware along with it and meet the functionality as well as the design constraints, timing constraints. Which one to choose? Maybe the 16-bit processor with special purpose hardware finally turn out to be less costly. There may be other issues also. That means both may satisfy the timing requirements, and we would like to choose the one which is likely to consume minimum power. So that's what we refer to as design space exploration. For the purpose of partitioning, we look at the tasks and we say that we shall have a task graph. Now this task graph is very similar to what you have seen as an activity diagram in terms of UML notation as well as task diagram in UML notation, but we are referring to this task graph as an independent representation model. So input to the partitioning process is a task graph that comes from system specification. Okay? In fact, that system specification we can represent using a variety of tools, using UML tools, and from there we can derive the task graph if required. Task graph is a directed and acyclic graph where nodes represent basic computation units. Can be programs in any programming language, because if I am using a programming language to specify the computational task here, what I am getting? I am getting an absolute unambiguous representation of the computation to be done at the node, that means to be done as part of a task element. Edges represent data and control dependencies. Okay, that means this data is required here, so there is this dependencies between the tasks. Okay. Now your basic partitioning problem is what? Mapping of these tasks to either hardware or software. Okay. Now, we may not like to go straight away or jump into this partitioning process, because we might do some transformations on the task graph itself to make the whole process more efficient. So, the task graph has got nodes. Nodes will have associated with attributes to specify the design constraints. This is an example of an attribute specification, timing parameters. So, I say that T1 arrives at 0, that is a starting point, and its deadline is 7. That means it must be finished within a time unit 7. That I can put in appropriate units associated with the time interval constraints. Now, if we are talking in terms of mapping of these task graphs into hardware elements, there can be other attributes which may become relevant. Hardware area, if you are designing an ASIC, what area is required? This may be measured in terms of the total number of gates required. Gates would translate to the number of transistors. What is the integration technology that you are using that will give you the total hardware area that may be required for implementation of a node in hardware. Then hardware execution time. If we are mapping into software, we can estimate what will be the memory requirement by this node. Okay. Then what will be the software execution time? The software execution time will come from architecture mapping. That means depending on which processor that you are using. Okay. That means you can realize that the moment I am searching for different alternate designs, that is I am exploring my design space, I can have the task graph associated with different attributes. So, I can have different instances of the same task graph with different value of the attributes associated with the nodes, depending on the kind of partitioning that I am considering. Edges also can have attributes like communication time, okay, because if we are thinking in terms of mapping the task to different processors, and if these processors are connected via network, then what would be the communication time? Then number of times the communication takes place, how many number of times the communication has to be done. In fact, we can also have with the nodes the number of times a task has to be repeated, because if you remember, we said that this task graph we are modeling as an acyclic graph. So, the repetition of a computation has to be indicated as an attribute for the node. There are other features which can be used in the context of the task graph. There would be I/O operations occurring. So, how to indicate I/O operations? Which task will require I/O? So, that is indicated by this kind of a node. Okay. This is indicating that T1 requires an input, T2 requires an input, and T5 produces an output. Tasks can actually share resources. In fact, if you see that these T2 and T3 does not have dependencies, so they can be concurrently scheduled. Okay. If they are concurrently scheduled, is it that they will require a shared resource? If we want to indicate that they are dependent on a shared resource, we can indicate the shared resource in the task graph itself with this kind of a model. So, this indicates that there has to be a shared memory between the tasks T3 and T2. Next comes, how do you represent the nodes? We have talked about attributes of the nodes, and we said that the nodes really represent computations. Okay? And if the nodes represent computations, that computation can be expressed in terms of any programming language. In this context, we are considering, in today's lectures, we are considering the representation in terms of imperative languages, that is procedural programming languages. And there can be models for representing computations that is to be carried out at the nodes. The two basic models which are used, one is your data flow graph model, another is control data flow graph models. In fact, these models are also used by compilers for the purpose of optimization of the code. So what is a data flow graph? Data flow graph basically represents a sequence in which the data is processed by a code. Okay? It does not represent therefore control, and it models the basic block, the code, with no entry or exit. Formally no entry or exit. There has to be although an entry point and an exit point, and through this you can describe the minimal ordering requirements on operations. So let's take an example. This is a simple assignment set of assignment statements. So these can be the computation needed to be done at a node. Okay. So this is a basic block. Now this block can be rewritten where I have introduced another variable. Why? Because y was being used twice. Okay. Instead of that, I am using another variable y1, so that each variable has got a single assignment. Okay? Each variable has got a single assignment. Now what is the implication of this? Let's look at the basic data flow graph. If we have this, you can understand that this is a sequence of assignments and this is your data flow graph. What it is showing you is that if you have got variables a, b and c, d, then these operations to take place, and this is indicating a dependence. Okay, this is indicating a dependence, and this is another dependence with respect to y. So what you can realize is that the moment I have got this y replaced by y1, I can make this computation independent of this step, because otherwise I would have to synchronize between the two. I have to do y equal to c minus d first, and then I had to do z, then only I could have done y equal to b plus d. By doing a single assignment, I have reduced the dependencies. Okay. Now these dependencies can be used for optimization of the code, scheduling of the operations, reordering of the instructions when we are mapping the computation onto a software unit to be run on an embedded processor. Okay. This can be even used if I am trying to design a hardware to implement this set of operations. Okay. But the basic point is that this data flow graph is a model to represent this computation. So what we are talking about? We are talking about a task graph where each node represents a computation, and we can represent the computation to be done at each node in the task graph by a data flow graph. Data flow graph is one such model. Now we can have more such models. So here is a partial order that we have got. So effectively, what does it mean? Can do pairs of operations in any order. Okay. So that means the instruction, the point I was telling, the instruction scheduling can be done. And why I would like to do instruction scheduling? Maybe to optimally use my pipeline processor. So another representation is control data flow graph, okay, which is another model, and CDFG represents control and data. In fact, any computation is truly can be modeled by control data flow graph, because tasks themselves are just not data flows. There will be control decisions which will be involved in each task element. Okay. So a task element would be naturally modeled by a control data flow graph. There are two types of nodes obviously now in a control data flow graph. One is a decision node, the other is data flow node. Data flow nodes are nothing but actually your data flow graphs being represented as a block. So a data flow node encapsulates a data flow graph and write operations in basic block form for simplicity in the CDFG. Now these can be again decomposed into your data flow graph. The graph in terms of nodes where each node represents an operation and I have input values with respect to that graphical representation. The control steps or the decision steps can be shown in this kind of a form. So you can find out it's pretty similar conceptually that of your basically your flowchart representations. So you have got this condition false and true. This can be multivalent conditions like your case statements. They can be represented in an equivalent form because a combination of these can be represented by this kind of a structure. So if I take an example, this is an example of a case statement, if then else and a case statement. So I can represent these as a control data flow graph. Now each of these are nothing but functions. Now corresponding to the functions I can again have a CDFG, okay, and that CDFG will replace this function, fine. And if I have a simple assignment kind of a thing, then that assignment block can be modeled as a data flow graph. This is an example of a for loop, okay. So I can represent a for loop or a while loop, you know they are equivalently represented, and this will be their representation in a control data flow graph. So here this is a simple single assignment statement which is a data flow node. Now what to do with these kind of representations? Okay, the basic idea is once we have these kind of representations, we can now try to look at various kinds of transformations which can be applied onto this model to make your code or the computation task at the nodes more efficient. This is the basic objective of having these kind of modeling techniques to represent computation tasks at the nodes. So we say that we shall do some kind of high level transformations. It's not that all these transformations will be applicable under all possible conditions. Okay? It may be that some of the transformations are applicable, some of the transformations are not applicable. So depending on the problem that you are considering, you have to look at these possible transformations of the computations scheduled to be done at each task node. First we shall look at loop transformations. That means whenever there is a loop, whether I can change these loops. So loop transformation, the basic objective of the loop transformation is to reduce loop overhead, increase opportunities for pipelining, and improve memory system performance. Because if I can reorganize the loops, all these advantages can become apparent. If these advantages become apparent, what is the consequence? If I can reduce loop overhead, the time required for execution of a loop at a node will be less with respect to an architecture mapping. That means after it's being mapped onto a particular processor, then I can meet the design constraints or the timing constraints for that task. Otherwise, the problem would have been that I need to think about a special purpose hardware to implement that code such that the timing constraint is satisfied. Okay? So basically you can understand that these transformations are critical so that your hardware cost may be reduced and you can be able to meet your timing constraints. The timing constraint is not only the one issue, other issue would be energy. If you remember, when we discussed cache memory, we said that cache misses would be a source of energy consumption. So I would like to maximize cache hits. So is it that by these transformations, can I maximize cache hits if I look at a software implementation? And if I maximize cache hits, I have savings both in terms of time as well as that of the energy. So if I can do that and I can meet the constraints, I shall not map possibly that task onto a special purpose hardware. I shall do that task on my processor that I have chosen, so it gets mapped onto a software. Okay. So these transformations are critical for these purposes. So let's look at the different kind of transformations that we can use. The simplest form of this transformation is loop unrolling. Okay. So this is an example to explain the loop unrolling. The objective of loop unrolling is to reduce loop overhead. This is a very simple loop. Okay. Now what is loop overhead? Loop overhead comes in corresponding to this statement, because this statement will be translated to a set of machine level instructions. Those set of instructions have to be executed each time the loop is executed. If I can reduce the number of those instructions, or if I can reduce the number of times these instructions be executed, then I can reduce the loop overhead. So let's look at this possible solution. So what has been done here? I have reduced the number of iterations. In the process of doing that, what I have done? I have actually multiplied, okay, used these array indices in a different form by multiplied by 2, okay, and this is 2 plus 1. So effectively I can do the same computation using less number of loop iterations. Okay. So the loop overhead goes down. Now we can say that you have introduced this many multiplications. But actually if you remember, say, ARM architecture, these are not really multiplications. They can be done as part of the same instruction itself because of the barrel shifter. Okay. So I get a much better optimized code for loop. Okay. So this is the basic idea of loop unrolling. Fine. Reducing the overhead of loop execution, because loops occupy a very large part of your execution time period, because you actually execute codes in loops. Okay. If you profile, you will find that the time required for different loops vary. Fine. And major part of your time for execution is spent in loops. So if we can really optimize the loops, then we can really get a advantage in terms of meeting the timing constraints of the design. Next operation or transformation that you can have is loop fusion. Okay. So if we are looking at the loop fusion, fusion means combination of the two loops. Fine. So here we have got example of two loops. Okay. And obviously the advantage that I shall get is that this code corresponding to the loop overhead will be executed once. Okay. And the interesting feature is, if it is executed once, then this loop overhead is being reduced to 0. This instruction had a loop overhead and this can be reduced to 0. But please keep in mind that I have although given these kind of examples one after another, okay, and it became obvious that we can combine this into two loops, these two loops into one, but this is not always obvious in the code. Okay. By looking at your control data flow graph, you can find out whether there are dependencies between such loops. If there are no such dependencies, you can decide to combine the loops and get what is called a zero overhead loop for some of the cases. In fact, other interesting thing is that once we have done this, literally I can reduce it to zero overhead, because if you remember, many of the DSP processors have support for zero overhead loop. You have to initialize the corresponding counters, okay, or the registers with the value of the number of counts, and in hardware itself the loop implementation is provided. So once I can do this combination, I can therefore further optimize the code depending on the architecture that I am using. Okay. So that's why this kind of analysis of the fusion becomes critically important. The other part of the fusion would be fission, or breaking up the loop, or distribution of loop into two. Okay. So this one of these approaches which is used is called loop tiling. Okay. So what happens in loop tiling? In loop tiling, you break one loop into a nest of loops. Okay. Now what is the objective of doing it? You can say that if I am breaking one loop into a nest of loops, what I am doing? I am actually increasing the loop overhead. So whatever I have discussed so far, am I contradicting it? It's not so. Okay. It may be required to have better control of locality of reference. Okay. So what is meant by why locality of reference is important? Locality of reference is important for cache access. Okay. Say for example, if I have a big array, okay, and I am doing some computation at each element of that array, what happens? After some set of updates, there may be a cache conflict and cache has to be replaced. Again, maybe in the next statement, I have to go back to the initial elements. Again, a cache conflict would come, because that by nature, the single loop violates the condition of locality of reference. So I might like to split that loop into multiple nested loops such that in each nested loop I satisfy the locality of reference. That means once that inner nesting is completed, then only the cache violation can come in. So I am liking to use the cache. That means I would like to restructure the code so that I can have a maximum use of the data that I have loaded onto the cache. So it changes, in that case it can change the order of accesses within an array, and it obviously if I change the order of access, it changes cache behavior, and if I am looking for change in a cache behavior, I shall be interested in improving its behavior and a better cache control. We shall see an example now. Let's look at this. This is a very simple operation, okay, that is I am multiplying. This is two elements of an array. This is a two-dimensional array and this is an one-dimensional array. Now you can realize that if I am doing so, what can happen? I can actually miss out on the cache, because this array Aij is a 2D array. So I might be going, depending on whether it's organized in a column measure or a row measure form, depending on that, it might be so that there are cache conflicts. Okay. So while the loop is being executed, I'm processing, so this is J is an inner loop. When I'm processing this, there may be multiple times when the cache conflict occurs, because I have to load the values corresponding to the J index changes, okay, and again I comes in, so there may be multiple conflicts here, okay. So what I would like to restructure that array. By restructuring the array, what I am telling is, I talk in terms of tiles, okay. These are tiles. So what I am telling here is that I won't like to cover each and every element. Here what is happening, if it's a if this J indicates a row, okay, so I am finishing off the row first, okay, then I am loading the next column. But if I restructure the array, I can actually do this operation with respect to part of the row, okay, or I can do it for one row and not all columns but part of the columns. So here the example is, this is say one complete row, fine. What I am doing part of the row, coming back, doing the next next row, then doing the next row. So I am moving along the column, before completing one complete row. Fine. And then I am going back and again doing the computation. So I have created what we call tiles, okay, and I have changed the order of access of that array. Now how to do that? If you look in here, the way I have reorganized the indices, what it's providing for? It's providing for access of parts of it. So I am now, if you see here, this I am incrementing I in steps of 2 and not 1. I am incrementing j in steps of 2, and here I am assigning this II, which is a new index, and jj, which is again a new index which I have brought in. And using these two indices, I have introduced an inner nested loop. In fact, in that inner nested loop, the II for a particular value of j, okay, if I assign a particular value of j and particular value of I, this goes from I plus 2, the minimum of I plus 2 to n. Fine. So I have created tiles of size effectively from 2, I equal to, if you say I equal to 0 and j equal to 0 at the beginning of the loop, then II is 0, jj is 0, and what will be the terminating value? Terminating value is 2, so it will go to 0, 1, 0, 1. So I am basically looking at the tiles. Tiles consisting of the two elements for row as well as that of column. Is this clear? So I have actually created a tiles because the array organization may be such that I can fit these data into a cache. So once I have completed this data, I won't like or I won't need to come back to use this tile again. Okay, this is the basic advantage. Fine. So what we have got in the process? We have increased the loop overhead. But I am reusing the data which is there in this tile. Okay, that means I am completely doing the tasks that I needed to do with the data in this tile. Since I have finished that task, I can move over to the other tile and reduce the number of cache conflicts. Okay, so the point that you should keep in mind that these loop transformations that we are talking about, all of them cannot be blindly used. They have to be used depending on requirements. I advocated first the loop unrolling to reduce the loop overhead. Now I am talking about splitting the loops, increasing the loop overhead definitely, but it would actually lead to improvement in performance because cache conflict reduces. There are various other ways of loop optimizations as well, because loops are good targets for optimizations because as I told you, a large amount of time is actually used in the loops only. So the loop optimization techniques which are followed are code motion, induction, variable elimination, string reduction. Now many of these are actually done as part of your compilers as well. You might not need to do before the compiler comes in. The simplest thing is this code motion. I did not do this evaluation every time as part of code execution, that means as part of my loop overhead. Okay, so I am removing it from here altogether and taking it outside. Okay, so these can be part of your initialization. So I am reducing the number of multiplications that you need to do. The moment I reduce that number of multiplications, the time required would be less. Then what we call an induction variable elimination. An induction variable is typically derived from the loop index, okay, because here you see that this is a two-dimensional array z and bij, and I am doing an assignment using the same index pattern. Okay. So for each assignment, I need to compute the address of these data elements. The computation of an address would imply a multiplication, this is I into m plus j, if this is the organization of the array. So for this address calculation, I need to compute this. So this would be done as part of the code required for this assignment. So what I can do is, I can use this expression directly, because this expression will be computed twice, once for z, once for b, if I directly use this code for mapping onto the software onto a processor. Okay. Now I might like to avoid that, because that would be a redundant computation. So do that. So you identify an induct variable, initialize to 0, and increment at the end. So if I do that, then I need not do this computation for this assignment at every step. So what we say, rather than recompute I into m plus j for each array in each iteration, share induction variable between arrays and increment at end of the loop. Okay. So this induction variable elimination can reduce this kind of timings. And in fact, you will find that these kind of operations are not very uncommon, because if you remember the code that you write for, say, your matrix multiplication, okay, there you would like to have similar kind of constructs, and matrix multiplication is a very common code for variety of operations. Next thing is cache analysis. In fact, the first part of the cache analysis we have discussed in the context of the loop nesting itself, that we would do nesting one inside the other and change order of accessing array elements and expose new parallelism opportunities, reduce the cache conflicts. And perfect loop nest will be the one where there are no conditionals in the nest. If there are conditionals, there may be data may not be properly reused. And because loops use large quantities of data, cache conflicts are common. And that's why this loop nesting is an important operation, okay, for dealing with this cache behavior. Let's look at another example. This of an array conflict. We have all studied set associative cache. Let's consider that I am dealing with two arrays, A and B. Fine. If I am dealing with two arrays A and B, and if it's a set associative cache, the mapping I am showing here is that this array A00 starts at location 1024, B00 say starts at location 4099. And the mapping is such that the three elements 1024 to these, okay, in fact this whole line in the cache is mapped with respect to this. It's a set associative cache, so a set gets mapped. So this entire set gets mapped here, and interestingly that B00 gets mapped to this point. That means the locations around B00 would be mapped to this line as well. Okay. So that means if I am accessing the array element A00, I have to access actually this entire cache line. That means when the data is loaded, this entire set gets loaded starting from say 1024. When I am accessing B, that same set in the cache gets loaded, okay, with entries at memory locations before B00 and ending in first location in B00. So when I am executing this loop, what happens? At each and every step, I shall have a array conflict and a miss, okay, so which is not at all desirable. So what is required? The solution could be reorganize the arrays, reorganize the data structures, okay. Now that reorganization implies what? One possibility is change the address of B00, try to move around B00. But that may not be always possible because of other arrays and other constraints. So other option is what you call padding. You pad an array, okay. So that means you add additional elements to an array, okay. So the solutions of this kind of a conflict is move one array or pad an array. So let's see what we really mean by padding an array. This we shall look at with an example of this a two-dimensional array, is A00. Okay. Let's look at this array A00. Now, this has got 3 elements per row. Okay. And therefore, if you look at this, I have got A00, A01, A02 and A10. So, if I have a mapping to the cache map is in this way. That means these 4 elements gets mapped onto one cache line. Fine. Now, what is the problem can happen? If I am actually accessing this row, okay, there won't be any cache conflict. But for each access of the next row, there will be 2 cache loads. Okay, if I am loading this for each of these row, there will be 2 cache rows or cache conflicts. Is this clear? Because you are actually having the mapping such that on a cache line, elements from 2 distinct rows of arrays are getting mapped. So, what is the solution? Solution is you pad an element. That is, you pad an element A02 here. This is a dummy element. Okay. That means you are changing this data structure itself. Why would you add this dummy element? It's very obvious. That means when I am doing computation on the first row itself, okay, I shall be doing the computation. Once I finish that and come to the second row, the second row as a whole gets loaded here. Otherwise, what would have happened? I would have got the data over here and then there would be a conflict and I need to come here and do the job. So, for each row actually would have required accesses, fine, which would lead to more number of cache conflicts. Now, since I am padding an array element, I am reducing the array access, okay, cache conflicts corresponding to the array access. So, add array elements to change mapping into cache and reduce the cache conflicts. Is this clear? So, that means when I am running a loop, you can understand when I am running a loop, this first element, when I come to access this first element, I might find out that it is in the array. When I come to the next element, there will be an array conflict. Okay. Now, if I am not doing anything with the first element, first row, and if I have to do an operation on this element, I have to do a cache load once. When I am going into the second element of the first row, again I have to do a cache load. But if I do this padding, I need to do it only once. Okay. So, array padding is another way of array transformation to use an optimal, to have an optimal use of cache. The other point is function inlining, which is another transformation. So, you replace call by function body. If you have a call in your computation, you replace it by the function body. Obviously, it is a low calling overhead, the putting into the registers onto the stack, etc., are avoided. But obviously, you can understand that not all functions are candidates, because it can lead to code size explosion, which you do not want, and therefore, it requires a careful manual identification of which functions can really be put onto the main code. In fact, it has been found that if you can do judiciously function inlining, your computation speed shows definite improvement, because time taken for this overhead is substantial. Why? Because you are accessing the memory, because a major point is you are accessing the memory to save the registers. Okay. So, if you are avoiding the time taken to save the registers for small functions, then your time required for execution of your code can substantially go down. And that is the basic point or the motivation for looking at function inlining for optimization of computation. Related to this is the problem of optimizing for program size. If you are looking at a node, a computation, I need to optimize for the program size. Now, the other point comes in. just try to understand these trade-offs. In the other previous case also, we have looked at trade-off with regard to the loop unrolling vis-a-vis loop nesting. We are trying to look at function inlining vis-a-vis optimization of the program size. If I am doing function inlining, I cannot do optimization. Okay, so but I need to do an optimization because I would like to use minimum memory, because that's also is a constraint for a design. So if I optimize the program size, I reduce hardware cost for memory and reduce power consumption of memory units, because I shall be using less number of memory units. Obviously, there are two opportunities to look at data as well as that of the instructions. So how do you reduce the data size? Here you use what we call the basic principle of reuse. Reuse constants, variables, data buffers in different parts of the code. Okay. Obviously, this violates again a basic software engineering diktat, which says that you should use different variables. Names of variables should be all distinct for different applications. But different variables should essentially mean what? Allocation of a space for those variables. If you can reuse variables, then the space required reduces. Okay. So variables, data buffers, you need to reuse at different parts of the code. The other strategy which is followed in many of these embedded systems, you generate data using instructions. That means you get a task node for generating data using instructions. Okay. So if you need some special kinds of instructions for an application, try to model the data using instructions. What is the advantage? The instructions would occupy less memory. Instruction goes into, say for example, flash. So the amount of flash memory required would be less. Okay. But when it is generating the data, you can say that, okay, data size would be large. Fine. If the data size is large, we can accommodate the data in a DRAM. Okay. But the point is, I might not require the entire data for all computations. Okay. So I need not have the complete data stored a priori, write a program to generate the data depending on requirements. Okay. In fact, the very common trade-off is, if you look at a very simple example of a trigonometric function computation, I can use a table driven approach where I use a table, and using a table I do a table lookup and get the trigonometric value. This will be fast, but obviously it will be memory intensive because I have to store the data in the memory. The other option could be, I can use a code, okay, special algorithms to evaluate trigonometric functions. Okay. The moment I do that, I avoid the memory for storing the data. So the reducing code size is, the basic strategy here is avoid function inlining, choose CPU with compact instructions. In fact, ARM shows an example, and use specialized instructions wherever possible. Okay. So you know that from ARM example, say we can do a judicious mix of thumb as well as ARM instructions to reduce the memory required for the code. The other approach which is also used is called code compression. Use statistical compression to reduce code size and decompress codes on the fly. So that means, if this is my instruction, this is a coded form of instruction. So these instructions from main memory passed on to the CPU. CPU itself can have a decompressor. Okay. And after decompression, you get the actual instruction which is in the cache. The actual instruction can be a 32-bit, but my representation can be 8 bits. In fact, I can use any form of entropy coding, a variable length coding, for instruction compression. In fact, a very common example of this, if you remember, we had discussed use of Java, that J2ME, and for J2ME you use a archival format of the code and not the standard format, where the binary code is actually compressed so that it can be loaded onto a small memory in the embedded system. So the next part is the floating point to fixed point conversion. What is a floating point representation? You have a mantissa, okay, and you have exponent. Depending on the value of the exponent, you can have variable precision. When you have a fixed point, that is not there. You have a fixed number of digits allocated for your fractional part. When you do that, what are the advantage? Obviously, you have got lower cost, computational overhead is less in terms of hardware, faster, lower power consumption, and that is what is suitable for portable applications. And obviously, the problem is if you have a finite word length effect, unless properly scaled, you have overflow and excessive quantization noise, okay, and it requires extra programming effort. But the fixed point conversion, why it is done as part of computation units, if you remember, many of these processors do have an support for fixed point arithmetic. Even the DSPs have support for fixed point arithmetics, and if you have to go for a higher cost DSPs, you have to have a floating point support in that for higher cost DSPs. Now, if your precision is good enough to have that you require for your application is good enough to be done with fixed point arithmetic, then it's better to go for fixed point arithmetic. The next thing which comes up is the concurrency management. If you have a granularity of the tasks, so these are the two tasks, we can merge the tasks. Okay, now we are again coming back and looking at a task level graph. Again, we can have a splitting of the tasks. If I split the tasks, this is task T2 was waiting for the input, but there we have isolated out one part of the task which does not depend on an input. By doing it, we have no blocking of resources while waiting for input. We have got more flexibility for scheduling and improved results. There are other representation tools. We have primarily looked at task graph. There are other representation tools which have been used. Process networks, which is in this kind of a thing. So you have a pressure sensor, humidity sensor. It's a multiplexer, goes to the FIFO, that is a data representation in a set of communicating processes. In fact, task graph is a more detailed representation of process networks in a way. So what is important here is you get various dependencies indicated. So this is another representation tool. Associated with this is called Khan process networks. In a Khan process networks are executable task graphs. And you have got asynchronous message passing here, okay? And communication is assumed to be via infinitely large FIFOs. So that means the synchronization is taken care of through these FIFOs. These are all abstract models which are used. In fact, Khan process network is again an abstract model which is also used for partitioning tasks. But we have concentrated in today's discussions primarily on the task graph and transformations with respect to the task graphs. Process networks and Khan process networks are other alternative models. So today's what we have discussed is basics of hardware and software co-design, looked at models used for partitioning, and studied higher level transformations which can be applied to the nodes. Further details we shall explore in the next class.